Welcome to another video on the CubePython package. In this video, we're going to talk about processor sharing, which is a form of service discipline, a way in which service is completed and how people are selected, or customers, whatever units of flow. And processor sharing is when a given server might be concurrently or simultaneously even working on giving service to multiple customers or working on multiple units of flow at the same time. And so the most basic form of this is to say that instead of completing one customer at some rate, at some fraction of that rate, they're completing at 1 over n of their base rate, where n is the number of actively or currently served customers, that it gets split in multiple directions. Okay, so this has some interesting properties, but maybe before we get into that, let's just step quickly through the code that I've got here for the example. We're importing the CubePython package, of course. We define a network, and there's no new code here. I'll point out to you where there's some new code to specify processor sharing. All of this should be familiar if you've seen previous videos, except for right here, where we're defining a node class to be of the PS, or processor sharing node class. By default, if you just pass in directly a node class like this, it is going to mean all nodes are of the processor sharing type. This network only has one node in it. You can tell by the length of these lists. But if you wanted to have different classes for different nodes in a multi-node network, you could do something like maybe just the first one is a processor sharing node and the second one is a ordinary node or something like that. But here we'll stick with processor sharing. It's a trivial kind of case here. Okay, so all we're doing here is we're simulating until a maximum of 1,000 customers has been completed, which is a little bit different than our usual approach of simulating until the max time. And it's because here we want to say, well, for some given amount of customers, how much time did that take? For a given amount of customers, is the average rate better? So we get all the records, we collect the service times. We're grabbing records that are later than 50 just for warm-up, and then we're printing the end simulation time, because remember, when you're simulating until max customers, the end time of the simulation is not fixed, which is different than simulating until maximum time when the end time is fixed, but the number of customers might be variable. And then here we're calculating the average service times, and then we're repeating this for just the ordinary FIFO. So here in the simulation definition, in initialization call, we don't pass in the PS node class. The rest of this code is basically the same, and we're just printing FIFO instead of PS. So let's run this code. And take a look at the results. So the rows here are, processor sharing and FIFO. For processor sharing and FIFO, they share exactly the same amount of time that it took to serve the 1,000 customers. Why is that? The reason for that is, first of all, we set the seed number in both cases to the same seed number. But that's kind of just to say that we're interested in the deterministic behavior. We want to fix the seed to say, well, when this runs under as close to the pseudo-randomness reproducibility as you can get, do we get similar or different answers? And we actually get the same answer. So the total time, or the total throughput, is weirdly unchanged, but the average rate on a per customer basis is different. So when we look at the average service times, you can see that the processor sharing is 1 out of 5 for the rate, approximately 0.19. And for FIFO, it's actually approximately 1 over 9, or 0.11 in this particular seed number. So you can get differences where the distribution is changing some of its properties, but the totals might be the same. Now, for those of you who have thought about averages versus totals, keep in mind an interesting property is that averages by construction are proportional to the total. So what you know is that you've changed the average, but you have to have changed something about the total time. And so it's like a redistribution of sorts that happens. Okay. Hopefully that was useful. I probably should have thought more for this video on examples when it comes up, but one imagined situation is when you basically have maybe emergency staff that have to be rapidly switching tasks, and instead of maybe between two different tasks like patients maybe, for which in theory you could try to model in more detail the switching of those tasks, but the processor sharing might be just a way of saying, well, spread out over the time, you get kind of this cost, this kind of concurrency cost to how much time it takes. So, all right, with that, best of luck with your discrete event simulations using the CuPython package, and I will catch you next time.